The air that surrounds the Earth is almost always moving. Air itself is invisible. What we see is not moving air, but things being moved by the air. If we light a smoke bomb on this beach, we will be able to observe how the air here is moving. The smoke indicates that air is moving from the ocean toward the land. Since it takes a force to make air move, some invisible force must be making the air over this beach move. What is this invisible force? Here in the laboratory, we can find some clues as to what causes wind to blow. This is a plastic box filled with the same air that's in the room. A piece of rubber with a handle attached to it is stretched across the airtight lid. At this end of the box is an open valve and a source of smoke. Watch what happens when we press down on the lid. Air moves out of the box into the room. Here are a couple of simple pressure gauges. Any pressure on the rubber cover can be read on the scale. The gauges show that there is no more pressure in the box than there is in the room. Now let's close the valve so that no air can enter or leave the box. When the rubber lid is pressed down, the gauges indicate that the air pressure inside the box is higher than the air pressure outside the box. What will happen if we open the valve? The air pressure inside the box is again equal to the air pressure outside. Now let's close the valve. Look what happens to the air pressure inside the box. Why is it low? When the rubber lid is pulled up, the volume inside the box increases. And since no air can enter the box, the air inside the box must expand to fill up the increased space. With the air pressure in the box lower than the air pressure outside, what do you think will happen when we open the valve? As before, air flows from a region of higher pressure to a region of lower pressure. Could it be that differences in air pressure cause natural winds to blow? This is a barometer, a sensitive instrument for measuring very small changes in air pressure. When the small needle is centered, the large needle indicates the air pressure in millibars. The air pressure on the beach right now is 1,013 millibars. 20 miles out from the beach, at the same moment, the air pressure is 1,014 millibars. And 20 miles inland, at the same moment, the sea level air pressure is 1,012 millibars. So, as we might have expected, the wind is blowing from a region of higher pressure to a region of lower pressure. Why is the air pressure over the water higher than the air pressure over the land? Here is a sealed plastic box in which we can simulate the conditions we found at the beach. This tray of water represents the ocean. The temperature of the air over the water is 72 degrees. This tray of dark soil represents the land. The temperature of the air over the soil is also 72 degrees. The smoke plume shows that under these conditions, the air in the box is not moving. Now let's repeat the experiment under conditions more like those at the beach. This lamp, like the sun, will supply heat energy to the water and soil. After 15 minutes, the temperature of the air over the soil has risen from 72 degrees to 95 degrees. The air over the water, however, has risen to only 80 degrees. This difference in temperature rise indicates that soil heats up more readily than water. As a result, the air over the soil becomes warmer than the air over the water. Now a current of air is moving from the water toward the soil. You remember at the beach the wind was also blowing from the water to the land. The air here is behaving just as the air in the box does. And notice something else. The warmer air is rising and the cooler air is falling. This discovery that a local wind is part of a larger circulation of air raises still another question. Why does warmer air rise while cooler air sinks? Here are two identical flasks. They contain exactly the same amounts of air and therefore weigh the same. The temperature of the air in both flasks is the same, a little over 72 degrees. Watch what happens when we heat up the air in the flask. The heat causes the air in the flask to expand, and some of it escapes into the balloon. Now the flask we heated weighs less than the other flask. When the air in the flask was heated, it expanded and became less dense. The scale shows that the less dense air is lighter. Now we have a clue to what happens when we apply heat to the water and soil in the box. As the air over the soil becomes warmer, it becomes less dense and lighter than the air over the water. So the cooler, heavier air over the water sinks down, flows over to the other side of the box, and pushes the warmer air upward. The horizontal flow of air between two places is what we call wind. We saw earlier that when there is a wind at the beach, there is a difference between the air pressure over the ocean and the air pressure over the land. Let's see if there is a corresponding difference in air temperature at these two locations. First, let's take a temperature reading in the boat. The air temperature over the ocean is close to 62 degrees. and inland the temperature is almost 74 degrees. Now we have a more complete picture of the local atmospheric conditions. Over the ocean, the cooler air, being heavier, exerts a higher pressure than the warmer, lighter air does over the land. The wind blows from an area of higher pressure to an area of lower pressure. This onshore breeze, or breeze from the ocean toward the land, is a normal daytime condition at the beach in sunny weather. However, you know from your own observations that winds frequently change speed and direction. For example, a smoke bomb set off a few days later at the same beach at the same time of day indicates the wind direction has changed. It is obviously blowing out over the ocean. At the same time, a giant cloud of dust is blowing in the same direction out to sea. Why did the wind change direction? Where is the cloud of dust coming from? 40 miles inland is a scene that resembles a giant forest fire. However, what appears to be smoke is actually loose silt and dust being picked up and carried away by strong winds. From what we have learned about winds, we would guess that there must be a mass of cold, heavy air somewhere, forcing the wind to blow in this manner. Let's take some temperature and pressure measurements and plot a simplified weather map. This is where the dust is being picked up and carried away. Here is the beach where we set off the smoke bomb and saw the cloud of dust moving seaward. The direction of the wind is obvious. On a weather ship here, the temperature is 69 degrees and the air pressure is 1,014 millibars. At a weather station here, the temperature is 50 degrees and the air pressure is 1,029 millibars. And at a weather station here in Utah, the temperature is 24 degrees and the air pressure is 1,032 millibars. Cold, heavy air on the high plateau flows downhill toward the low coastal plains where the air is warmer and the pressure is lower. The result of this combination of conditions is that the air flows fast enough to move large amounts of sand and dust. A cloud of dust is being blown out over the ocean, and our smoke plume is being blown out to sea instead of inland as it would be on a normal sunny day. Local pressure conditions on the beach have been overwhelmed by a cold, heavy air mass flowing in from the northeast. Near the poles of the earth, the sun does not shine at all part of the year. When it does shine, it is always low in the sky, even at midday. Furthermore, the snow and ice reflect much of the sun's heat, so it's cold up here. Near the equator, the sun shines every day of the year. At midday, it is always high in the sky, and the dark ground absorbs much of its energy. So it is usually hot down here. The air is always being cooled in some places and warmed in others. Half of the earth is always being warmed by the sun, while the other half is in shadow. And, of course, the earth is always turning. It is no wonder, then, that the air around the earth is constantly moving. It is even possible that the moving air holding up this kite in California has traveled all the way down from the polar regions. Can you explain how this could happen? And where does the energy to move air come from?